So let's first discuss the uncoupled modal response history analysis procedure, and then we will use that procedure to understand the modal pushover analysis. So the UMRHA procedure can be seen as the natural extension of the classical modal analysis procedure to the nonlinear systems. The classical modal analysis procedure says that you have an elastic structural model, multiple degree of freedom system. You can approximately decompose its response into the response of first few vibration modes, and each mode is represented by a single degree of freedom system mathematically. So in the classical modal analysis procedure, we start with this governing equation of motion of the multiple degree of freedom system, mass matrix time u dot dot vector function of time, plus the C matrix times u dot vector function of time, plus K matrix times u of t vector function of time, equal to minus m times I times ug dot dot. This is the original governing equation of motion for multiple degree of freedom system. We uncouple this equation of motion into the single degree of freedom system equations, or in the uncoupled form, using the orthogonality property of mode shapes. So each of the uncoupled equation resembles the equation of a single degree of freedom system. So it's like mathematically we can decompose the multiple degree of freedom system into several single degree of freedom systems, each having its own time period, right? So the response of that multiple degree of freedom system, it can also be described as a sum of the responses of these single degree of freedom systems. So this is the basic idea of the classical modal analysis, or modal response history analysis, or mode superposition method, whatever you can say. In this particular method, we are decomposing our multiple degree of freedom system into several single degree of freedom systems. This idea is only applicable to linear systems. It is strictly applicable to linear systems. The concept of mode shapes doesn't exist in nonlinear systems. Mode shapes are only associated with linear systems, right? But we can invoke some assumptions. This uncoupled modal response history analysis procedure is based on the assumption that mode shape still exists in the nonlinear range. We can approximately use the same mode shapes for a nonlinear system which are associated with the linear version of that system. And they not only exist in the nonlinear range, they can still be uncoupled, or they can be assumed uncoupled, just like the classical modal analysis. So with these two assumptions, we can mathematically formulate this procedure called the uncoupled modal response history analysis. So just like the classical modal analysis, the idea is explained in the bottom here, that you now have an inelastic structural model which is subjected to an earthquake. So you approximately decompose that inelastic structural model into sum of few single degree of freedom systems, each representing a mode's contribution of that inelastic system. But each of that single degree of freedom system is not elastic anymore. It is also inelastic or nonlinear. So each of the single degree of freedom system have its own nonlinear force deformation behavior, which is governing its response. And now you apply the earthquake to each of that single degree of freedom system separately to get the fluctuating responses of each mode, and then sum those responses, just like in the modal RHA or classical modal analysis. You calculate the response of each mode separately and sum their responses and get the total response. but each mode is represented by a linear elastic single degree of freedom system in the classical modal analysis. Here in the uncoupled modal response history analysis, each mode is represented by a non-linear single degree of freedom system, and the dynamic response of each non-linear single degree of freedom system is determined and combined to approximately get the same response which you would get if you apply directly the earthquake to the non-linear multiple degree of freedom system. So it's like using the same concept approximately for non-linear systems also, while knowing that it is strictly not applicable, but when it is applied to some real cases, it showed very good matching with the nonlinear time history analysis, especially for structures which are not going into significant levels of inelasticity. So for lightly yielded structures, this assumption of uncoupled modal response history analysis may not result in a significant error, and it can still be used as an approximate seismic analysis procedure. So let's quickly discuss its mathematical formulation of the UMRHA procedure. For linear elastic systems, the UMRHA procedure will become exactly same as the classical modal analysis or modal response history analysis, because the assumption of UMRHA, they are valid for linear systems. They are approximate for or strictly not valid for nonlinear systems, but approximately they are valid for linear systems. So the classical modal analysis procedure for linear elastic system is equivalent to finding the response of the structure to the effective earthquake forces of each mode separately, and then combining or superposing the response for all vibration modes. So in the classical modal analysis, we calculate the response for each mode against the effective earthquake forces of those modes, and then sum those responses in the time domain directly to get the dynamic response of multiple degree of freedom system. So in that, we assume that when we apply the nth mode's effective earthquake forces, the response is completely in the nth mode only, and there is no contribution from the other modes, which means that we assume we actually use the modes uncoupled, they are not coupled. The response of one mode is not affecting the response of other mode. The application of nth mode's forces are not causing any response in the mode other than nth mode, right? This is strictly true for linear systems only, right? So the linear systems, when we say that the governing equation of motion for linear elastic multiple degree of freedom system, when it is subjected to nth mode force, the response will only be in the nth mode. So in the governing equation of motion, we can simply replace the total P effective with the nth mode's contribution of P effective, this one, and the response will only be in the nth mode. So U will only be UN, right? U sub n is the displacement response of the nth mode only. So no contribution from the other mode other than the nth mode. And this can be expanded in the modal coordinates, converted into modal coordinates using this expression. That is the famous classical expression from the modal analysis, that we convert the u coordinates into some new coordinates which are represented as q here using the mode shape vector. When we uncouple the governing equation of motion, when we put that in the original equation and we multiply the whole equation with phi n transpose and then use the orthogonality property of mode shapes, we can uncouple the governing equation of motion in this form. This is the nth mode's uncoupled equation of motion, which we have extracted from this multiple degree of freedom system equation. And this equation is same as the equation of a single degree of freedom system, which is subjected to this dynamic loading on the right hand side, and which has the natural frequency omega n, and which have the damping ratio xi n. So this equation mathematically is representing a single degree of freedom system for that nth mode, right? And this can be written for any other mode also. For any general nth mode, you can write it using this equation. So the response which can be calculated by solving this equation, because this equation for the nth mode at the bottom is in the q coordinates. So when we put that u into q coordinates in the original equation, we get this equation. This is same as the classical modal analysis procedure. So this equation can be solved for that single degree of freedom system equation, can be solved to calculate q of t, actually q sub n of t, and then that qn of t can again be converted into the original coordinates, which is the u coordinates. When you convert that, you get this equation. Now this equation is telling us that the nth mode's displacement contribution or displacement response of a multiple degree of freedom system is simply equal to the modal participation factor times phi n times dn of t, where dn of t is the response of that linear elastic single degree of freedom system, right? So there is one more step involved in that. We replace this qn with this equation, and then we get this final equation. So this is the nth mode displacement response, right? So you apply that earthquake to nth mode single degree, right? This earthquake is applied, whatever is the ug dot dot, and you get the displacement response of this mass, and that displacement response is d of t, actually dn of t, when you apply ug dot dot, right? So each single degree of freedom system this way, for n equal to 1 up till all degrees of freedom, we can calculate this dn of t by solving its single degree of freedom system and get the displacement response for all significant vibration modes. Actually not displacement response, but all other responses like interstory drift, like any other response. So let's represent Rn of t as the general response quantity coming from the solution of that single degree of freedom system of nth mode. So Rn is any response. It can be moment, shear, displacement, rotation, anything. So if you repeat that exercise for some enough number of mode shapes, then you can calculate, then you can combine or simply sum all the displacement or any other responses Rn of t. You can simply stitch them or superpose them and get the combined response R of t. Let's say moment in a particular element. From each mode you can calculate the complete history of the moment of each mode and then combine all those histories to get the total moment history of the complete structure. So this is exactly same as the classical modal analysis or modal RHA procedure. So UMRHA procedure for linear systems is identical to the modal RHA. But now let's use the same idea of the modal expansion of spatial distribution of effective earthquake forces and now apply it to nonlinear systems. When you apply it to nonlinear systems, it is called UMRHA, Uncoupled Modal Response History Analysis. So now in elastic systems, we know that the modal analysis is not valid actually, but still we can invoke some assumptions, right? So we can assume that the natural vibration periods and modes of the corresponding linear systems are the same as the vibration properties of the inelastic system undergoing small oscillation. So we assume that the nonlinear system have the same mode shape and time period which its corresponding linear system would have had, right? So if the same system is subjected to a vibration of very small amplitude, the same system would behave in a linear manner and it will have some mode shapes and time periods. So the method assumes that we will be using same mode shapes for a nonlinear system also. So the modal expansion of effective earthquake forces is also valid for inelastic systems, where now the mode shape vector represents the mode of the corresponding linear system. We know that the P effective earthquake forces for nth mode, they actually are based on the modal expansion phi n. So if we use the same mode shape as the corresponding linear system, we can approximately apply the idea of the effective earthquake forces for each mode. So now the same equation, but now the Ku term in the equation is replaced by a nonlinear function. So the same equation for nth modal forces, the same equation is written, but now the Ku term, it is not equal to Ku anymore. It is equal to some function between elastic restoring force and U. Now it can be a nonlinear function because the structure is nonlinear, right? So structure is still linear in damping. Inertial force term, it is already there. But the elastic restoring force is now replaced by a nonlinear function between elastic restoring force and deformation U. Now the solution of this equation is not simply this one, because modes are no more uncoupled anymore, right? So we cannot say that the application of nth mode elastic force, nth mode effective earthquake force will produce the response only in the nth mode. We cannot say that anymore because the modes are now coupled because of the nonlinearity. So they cannot be assumed uncoupled now, and strictly speaking, we cannot say that the nth mode effective earthquake forces will produce only the response in the nth mode, just like we say in the in the modal RHA or classical modal analysis. So now the UN of T will be actually sum of phi r into qr, where r can be 1 to n. So we know that the nth mode contribution, the response to this equation actually will have a contribution of more than one modes because of this coupling thing. So they are no more coupled. For linear systems, this QR of t was 0 for all other modes other than nth mode. So therefore we were getting this equation at the top, that nth mode response is contributed only by nth mode shape. But now it will be contributed by mode shapes other than nth mode also, right? So, but UMRHA procedure is based on the assumption that we can still assume them uncoupled approximately, or we can assume them weakly coupled, right? So this equation is approximately replaced by the same phi n into qn. So again, although we know that the original equation can be coupled, but we can assume that un of t can still be approximately equal to phi n into qn. The response against the nth mode effective earthquake forces can still be approximately in the nth mode only, and the effect of coupling can be ignored. This is the basic assumption of UMRHA procedure, and this have been shown by Chopra and Goel, that when you apply the effective earthquake force for any nth mode, the response of any nonlinear system is primarily in that mode only, even if it is nonlinear. So even the modes are strictly not uncoupled, still the response is mainly in that mode and the other modes are not excited much and their response can be neglected. Here, for example, in this figure, the P effective earthquake forces for first mode were applied. P effective 1 was applied to the structure, and the response you can see is mainly coming in the first mode. This is first mode displacement response, second mode, third mode and fourth mode for one particular structure. So when the first mode effective earthquake forces were applied, the response is mainly in the first mode. Second, third mode response is negligible or very small compared to first mode. Similarly, when the second mode effective earthquake forces P effective 2 were applied, the response in the second mode is significant and first, third and fourth is negligible. Same is for P effective 3. Only third mode is excited much, but first, second and fourth are not excited. And similarly, this is P effective 4. So Chopra showed that when you apply the effective earthquake forces of a particular mode, even if the structure is nonlinear, mainly the response is only in that particular mode, right? And the response contribution from other modes which occur because of the coupling of mode shapes in the nonlinear range, that can be ignored or that is negligible, right? So depending upon the validity of this assumption, UMRHA procedure can provide approximate or accurate results depending upon this assumption is valid for case-to-case basis or not. For lightly yielded structures which do not go into significant levels of nonlinearity, this assumption may still be valid and UMRHA procedure may still get very accurate results. But for heavily yielded structures, the assumption may not be true and it will be highly approximate. So although the natural vibration modes are no longer uncoupled, just like in they were uncoupled in the classical modal RHA, here they are not uncoupled. If the system responds in the inelastic range, if they are no longer uncoupled, modal coupling is weak. This is the conclusion drawn, that modal coupling, the effect of modal coupling is weak. So here you see 73.9 in the first mode compared to very small values in the other modes. Similarly, here significant number in the second mode, small number in the other modes, right? So the effect of that coupling because of nonlinear range is weak, and therefore if we ignore that, we can still have a method for nonlinear systems, right? So UMRHA procedure is based on this whole equation that Un of t is approximately equal to phi n into Qn. That nth mode effective earthquake forces will approximately produce response only in the nth mode, and the response contribution from other modes may be ignored. You put that equation in the same single degree of system equation, we get this form of the equation. And again, by rearranging and by comparing making it similar to the single degree of freedom system equation, just like classical modal RHA, we finally get this equation. This equation is now again the equation of a single degree of freedom system, but with one difference, and that difference is that here the elastic term is replaced by a nonlinear function which is Fsn. Fsn is a nonlinear function now. It is representing the nonlinear force deformation behavior of a nonlinear single degree of freedom system. So if I draw a single degree of freedom system, it is not represented by a constant k number. Now it is represented by a force deformation behavior which is nonlinear, F versus D, right? And now you can apply an earthquake to this system and calculate the response to that earthquake. That response will be representing the response of that particular nth mode of the multiple degree of freedom system. So you repeat that exercise for a significant number of modes and get the response for each mode in time domain, just like classical modal RHA, and then stitch them. Responses can be superposed, and then you get the total response of the inelastic system. Obviously it will be approximate because it is based on this assumption. So the issue is now that how to calculate that nonlinear force deformation relationship, which should be assigned to the modal single degree of freedom system. And for that we have to use what we call as the reversed cyclic pushover analysis of our structure. I'll explain that in a minute. So Dn actually may be interpreted as the deformation response of nth mode's inelastic single degree of freedom system compared to it was the response of elastic single degree of freedom system in the classical RHA. So equation is same, but now this dn will be coming from the nonlinear response history of an inelastic single degree of freedom system, no more elastic. So that single degree of freedom system is defined by original omega n and tn and xi n, which was of the corresponding linear single degree of freedom system, or the nth mode of the multiple degree of freedom system. And secondly, this inelastic single degree of freedom system is defined by a force deformation curve or relationship, and that relationship we can approximate by performing the cyclic pushover analysis of our building. We can apply the modal inertial earthquake, modal inertial load pattern to our nonlinear multiple degree of freedom system and give it cycles of loading and unloading and reloading and develop this force deformation relationship. So we solve that equation at the bottom of last slide, this one, nonlinear single degree of freedom system. We solve for each mode and calculate dn, and that dn can be converted to the response of multiple degree of freedom system using the same equation and any other response like story, drift, shear, moment, anything. So we repeat that exercise for enough number of modes, n equal to 1 to capital N, and extract the responses for each mode, and finally combine the responses, sum them to get the total response. This total response of inelastic system will be approximate response because it is coming from the superposition of the responses from several inelastic single degree of freedom systems which are approximately representing the response of each mode of that building. So therefore this UMRHA procedure is approximate for inelastic systems. So here in this example Chopra showed that on the left hand side you have the nonlinear response history analysis which is carried out for the nth mode effective earthquake forces n equal to 1, 2, 3, 4 for first mode, then for second mode, then for third and fourth. And then UMRHA is performed for n equal to 1, 2, 3 and 4. And UMRHA is giving almost comparable result compared to the nonlinear time history analysis, right? So here actually the response, the effective earthquake forces for any particular mode is applied and nonlinear time history analysis is performed, and then the response for a particular mode is filtered out and shown here. And then here in the UMRHA, the first mode is the response for each mode can be separately described by its modal single degree of freedom system, so you can directly compute them. So here it is shown that they are comparable, or they are, you can say, very close, peak response as well as the complete history. So this shows that UMRHA have the potential to be developed further as a seismic analysis procedure, but the main issue is that we can get an accurate force deformation behavior for each modal single degree of freedom system. For that we developed the idea that if we can perform the cyclic pushover analysis using the modal inertia load pattern of that particular mode and develop the cyclic pushover curve, unloading, reloading, the complete cyclic curve, That curve can be converted into a forced deformation behavior and given as an input to our single degree of freedom system, nonlinear single degree of freedom system, representing that mode. And we can do that for separate modes, several modes, and sum the response to get the combined total inelastic response. So this is the cyclic pushover analysis, that you apply some load in one particular direction. Like if I go back, so we apply load in one particular direction, then we change the direction and increase the amplitude, then again change the direction, again increase the amplitude. We keep on doing it. So every time we apply the loading, we increase the amplitude and reverse the direction. Using this, we can generate what we call as the cyclic pushover curve, that we load it up to level, then unload it and load it in the opposite direction, then again unload and load it in the opposite direction. So we develop these cyclic loops between base shear and roof displacement. So just like we do it for monotonic pushover analysis, here we are performing a series of analysis, but by reversing the directions and increasing the amplitude. With each cycle we are increasing the amplitude, right? And we are using the modal inertia load pattern m into phi. Let's say we are doing it for first mode, then we will be using our load pattern m into phi 1. For second mode, we will be using a pattern m into phi 2, right? So the load, the forces which we apply have the same pattern as the mode shape. This is called modal inertia load pattern, mass times the mode shape vector. So we do it for a particular vibration mode and develop its cyclic pushover curve. We convert that cyclic pushover curve into forced deformation behavior, which can be assigned to a single degree of freedom system. And then we model that single degree of freedom system. Actually, we have to first idealize that also, because exactly we cannot give it to a single degree of freedom system. We have to give it as a rule or an idealized hysteretic model. Then we give it to a single degree of freedom system. Now it is a nonlinear single degree of freedom system representing the response of that particular mode for which we perform that whole process. Subject that single degree of freedom system to earthquake and solve this equation. This is the equation of a single degree of freedom system, a nonlinear single degree of freedom system having a nonlinear forced deformation behavior. That behavior is coming from the cyclic pushover analysis against the modal inertia load pattern of that mode only, right? So we extract all the responses: displacement response of that single degree, force response of that single degree of freedom system. The displacement response of that single degree of freedom system is converted to all the other displacement responses of the whole building or multiple degree of freedom system, right? Similarly, the force response of that single degree of freedom system is converted into force related responses like shear, moment, everything of the multiple degree of freedom system. So we repeat that whole cycle for first few vibration modes and combine the responses in time domain to directly get the fluctuating response in time domain for nonlinear system. And that nonlinear system has been shown, that nonlinear response, combined response, has been shown to match well with the nonlinear time history analysis for several real buildings. So uncoupled modal response history analysis for elastic system, it is same as the classical modal RHA. For inelastic system, it is approximate method because it is based on the idea that the coupling can still be ignored between mode shapes. And it is based on two approximation. One is that the responses can be combined for each mode, superposition. This is strictly valid only for linear system, elastic system. It is not valid for inelastic system, but still we use that. And second assumption is the coupling, neglecting the coupling of modal coordinates, which permitted us to compute the response of inelastic multiple degree of freedom system to nth mode effective earthquake forces just using a single degree of freedom system of that mode only. So this approximation is reasonable only because the excitation is P effective nth mode's contribution to the total P effective. It would not be valid for an excitation with lateral force distribution different than Sn, pointing out that the modal expansion of effective earthquake forces is a key concept underlying the UMRHA. So this modal expansion of effective earthquake forces is the key concept on which the whole UMRHA procedure is formulated. So now I will quickly sweep through some of the results for a few example buildings when the UMRHA procedure was applied, the same concept, to few real buildings, and then I will show you that they are giving us quite close results or with reasonable accuracy compared to the nonlinear time history analysis. So these are the three buildings I will be using to demonstrate few results. It is first is 20 story, then 33, then 44 story. They are typical buildings located in Bangkok. They are existing buildings and they have several existing features like masonry walls and some irregularities also. Their nonlinear models were constructed. So the shear walls were modeled using multiple vertical line element models. The RC columns were modeled using lumped fibers located at both ends of the columns. Masonry infill walls were modeled using the equivalent concrete struts, and the nonlinear concrete and steel fibers were modeled using these constitutive relationships. These are the four different sets of ground motions which were used in this study. So I will not go into its detail, directly show you the results. So first we performed the cyclic pushover analysis of few example buildings, these three buildings actually, and we identified the force deformation behavior for each mode which should be given to its single degree of freedom system. So for first mode of this particular 44-story building, you can see this is the result of cyclic pushover analysis. The cycles of loading and unloading were given until the building is significantly damaged. So we get this cyclic base shear versus roof displacement or roof drift curve. Although this slide itself shows a lot of information about the progression of structural damage, the cyclic degradation in stiffness and strength, for example, but I'll directly skip to the UMRHA steps. So the first step is the cyclic pushover analysis of the nonlinear models using the modal inertia load patterns for first few vibration modes. So this is for all three buildings, the cyclic pushover curves for first three modes, mode 1, 2 and then 3. Similarly for 33-story building 1, 2 and 3. Again 44-story building 1, 2 and 3. So the cyclic pushover curves were developed. Then the next step is to idealize those cyclic pushover curves using some hysteretic model and assign it to a single degree of freedom system and apply the earthquake to that single degree of freedom system so that that particular mode's responses can be calculated. So here in this example, this is the idealized force deformation behavior which was given to a single degree of freedom system. In this example, it is 20-story building and first mode only. So the black line actually is the actual cyclic pushover curve, and red line is the response of that single degree of freedom system against an earthquake. So the exact matching shows us that the single degree of freedom system, red line, is representing the first mode of that 20-story building with a reasonable accuracy. So first mode cyclic pushover curve is a black line, and when we convert that black line into an idealized force deformation behavior, give it to our single degree of freedom system, run that single degree of freedom system and plot the response again on the same curve, we get an exact, near to exact matching. So this shows that our single degree of freedom system if it was for first mode, because the cyclic pushover was for first mode. So this single degree of freedom system is representing the first mode of this 20-story building with a reasonable accuracy. Similarly, we do it for second mode, third mode, fourth mode, and combine the responses of all these single degree of freedom systems, and that match well with our nonlinear time history analysis. This is for mode 1 of the first building, mode 1 of the second building, mode 1 of the third building. So we map the cyclic pushover curve to a single degree to represent that particular mode. We do it for all earthquake, we do it for all important vibration modes. This is for second mode, all three buildings. Then this is for third mode, all three buildings. One important you can say conclusion which you can draw from here is that each mode is not experiencing the same level of nonlinearity. Instead, the first mode is experiencing the most nonlinear level. The second mode is experiencing a relatively less level of nonlinearity, and third mode is almost linear elastic. Just in this B2 second building case, it is yielded but not significant. In this case, it is almost linear elastic, So which means that as we go to higher modes, they tend to remain elastic under the same earthquake. So all modes do not experience the same level of nonlinearity under the same earthquake. First mode experience the most, and depending upon the height of the building, sometimes second mode also may yield, but third and fourth mode may remain elastic, and higher modes may remain elastic. So this is a summary for another ground motion. Here you can see first mode significant yielding, second mode less yielding, and third mode almost linear elastic. So we calculated the responses from those single degree of freedom systems, modal single degree of freedom systems, using UMRHA. For first mode, this is the displacement, second mode and third mode also, and then we combine the time histories of these modes, modal responses, and get the envelope of the combined history also. We did it for displacement, then interstory drift, and then we also be for story shear and story moment. So now using UMRHA procedure, you can calculate the response for each mode separately. You can decompose the combined response line into the modal contributions. So first mode line, second mode line, third mode line, and when you combine the time histories and pick the peak number, you get the black line. So these are the story profiles for displacement, interstory drift ratio, shear, and then finally moment. Combined also, and for individual modes also. The combined line is then compared with the direct nonlinear time history analysis. Nonlinear time history analysis here in this comparison is shown with the black line, and the blue line is showing the combined response from first three vibration modes calculated using UMRHA procedure. And we see here that for this particular ground motion and for this particular building, it is showing a very good match. So just three single degree of freedom systems, when their responses are combined, they are matching with good accuracy using for this 44-story building. Almost the same response is described, which is described by the nonlinear time history analysis. So you can now compare the effort required to perform nonlinear time history analysis and then to extract the results, and then the computational time required. And for UMRHA, it is simply three single degree of freedom systems, each representing one particular vibration mode. Yes, that in UMRHA procedure, apart from running those single degree of freedom system, we also have to perform the cyclic pushover analysis first to establish their force deformation behaviors. But once we establish that, we can simply run those single degrees in a matter of minutes and then combine their responses to plot the combined response. This has been tested for different ground motion sets and for different buildings, and it is consistently showing good results In some cases the error is significant, but in few cases it is showing very good matching with nonlinear time history analysis. It all depends on the validity of assumptions on which this method is formulated. In this example, you can see that this ground motion is applied. This is the roof history determined from UMRHA procedure for first mode, roof displacement history against that earthquake. Second mode, roof displacement history. Third mode, roof displacement history. I stitch all of them. I just add them to get this combined roof displacement history. And you can see that it is matching well with the nonlinear time history analysis. So black line is the direct integration nonlinear time history analysis roof displacement, and blue line is the superposition of first three vibration modes as determined from the UMRHA procedure, and you can see that the peaks are matching well and also the overall trend in time history is matching. Obviously there is a mismatch at several locations, but that obviously may be attributed to the assumptions which make the UMRHA procedure as a approximate method. So the summary is that if we can accurately develop the modal hysteretic rule or model using cyclic pushover analysis first for each mode, then the UMRHA procedure can give us an accurate estimate of the seismic response of high-rise buildings. So the computational effort obviously is significantly lower than the time history analysis, and more importantly, more than the computational time, the insight which you obtain from getting the response of each mode individually is more important in understanding the behavior of that building. So you get the decomposition of response directly, which is not you can say available in case of direct integration time history analysis. So this understanding can be obtained when we perform that time history analysis, when we perform the UMRHA procedure. So that understanding which is obtained by looking at the response mode by mode, it may be translated into development of effective design strategies. For example, if you want to suppress a particular response, for example, here if I go back and show you the decomposition of dynamic response as given by UMRHA, maybe this figure. Yeah, this figure. So we see here that the second mode here, this red line, is having the most contribution towards the story shear. So if our purpose is to suppress the story shear or reduce story shear, we should focus on the second mode, right? If I go back and show you here, and here it is shown that the displacement response is mainly governed by first mode, right? So if we want to reduce our total displacement, we should apply some effective control strategy which reduce the response of first mode only. So any damper or any device which should be used, it should be tuned to the frequency of first mode so that the first mode can be suppressed, and as a result the total response will be reduced, right? So this understanding of getting the response for each mode separately, even for nonlinear systems, this understanding can be translated into development of different design strategies, right? Similarly, for interstory drift, you can see that first mode is participating the most. It has the most contribution towards the total drift response, right? But UMRHA procedure should always be validated with the nonlinear time history analysis, and it should be applied with care because it is an approximate method and it may give, you can say, it may have a significant uncertainty in its responses also if it is not properly validated against the nonlinear time history analysis for few cases, right? So that's all about the UMRHA procedure, and now let's towards the end, let's quickly discuss the modal pushover analysis because all of our information is complete now to understand it.